Good afternoon and welcome to the 10th problem solving session of the course Fundamental of Semiconductor Devices NOC 24E02. This is March 30th. My name is Amit. I'm a PhD student at ISC Bangalore. A very quick summary. Firstly, we talked about the classification of materials in terms of their electrical conductivity, that is sigma. We classified them as metal, insulators and semiconductors. Semiconductors are a peculiar brand of material in the sense that they have a band gap, which means that arises due to the fact that when different large number of, let's say, Avogadro 10 to the power 23 number of atoms of, let's say, silicon come together, their orbitals overlap such that they form two bands, in the sense that this is a continuous, so this is the continuum of energy, and let's call this level EC and this call this level EV. Below EV there are states available for electrons to occupy, and above EC also there are states available for electrons to occupy. That's what I mean when I say the continuous band of electrons. Okay, and this is the forbidden gap, in the sense that there are no electronic states available for the to be occupied. So electron cannot reside in this specific energy, and obviously the electrons can be excited across, let's say, from valence band to conduction band by, let's say, shining a photon. But please remember that all of this is happening, this electron is not free, it is in a periodic lattice, and we saw that we can represent that periodic potential by the Ironic Banney model is something like this. This is moment, the potential with respect to x, and when an electron is moving in such a periodic potential, what we saw is that now we can express the energy of an electron on the y-axis, and on the x-axis we have k, which is the wave vector given by 2 pi by lambda, and the same energy levels which we saw here, this is E versus x, energy versus x, linear space, this is reciprocal space. We can also express these as EC, as these curvatures EC and EV respectively, right? And this becomes now our band gap. All right, then we saw that there are energy states. So this is what I call the density of states, the number of states per unit energy and per unit volume. So for instance, you see in this band structure, E versus K is the band structure, there are different energy states that are available. So what is their density, how closely are they packed together? That is given by density of states, and for 3D system we saw it came directly proportional to the square root of energy. Also, just being the states here is not sufficient, the electrons also has to occupy them. So that was given by this Fermi function Fe over here. It's a probability distribution function, and it was written by something like this. It's an exponential dependence. So if the energy is higher than EF, the Fermi level, you can see the probability of occupation is less than half, and hence this is sometimes referred to as the Fermi level as the average level, let's say. Okay, just a second. Yes.
Actually,
Yeah.
professor
Yeah.
told that Fermi level is a statistical construct.
Yes.
How will you define? Actually, it is told that it is a maximum number of electrons occupying like that, but it is between the conduction band and valence band, and there are no electrons and no energy
Yes,
levels.
that's why I say it's a statistical construct.
Yes.
Think of it, it's a hypothetical thing. If such a level existed, what would have been the probability of occupation? So see, essentially this is a system. So Fermi level, as it happens, it also exists in metals, right? There the Fermi level definition is that the highest energy level that is occupied. Okay, in the semiconductor world, when we talk about, we tweak the definition and we say, okay, the Fermi level is that hypothetical energy level at which probability of occupation is half. We define it in such a fashion. It's not that it exists physically. You will not find that, okay, Fermi level lying a 0.7 EV below the conduction band. Okay, that is a Fermi level, and somehow due to some techniques you find, let's say, if there are some electrons there or not. No, you will not find any electrons, because that is forbidden. That is literally the point, energy gap or band gap. There are no energy states available. Ideally, actually there will be defect states and whatnot, but we're not talking about that here. We're talking about a perfect crystal, perfect material, and so on.
So the statistical construct is exactly for the semiconductors.
Yes. For metals,
but for metals, it is the maximum number of occupying.
Not the maximum number, the highest level that is occupied, not the maximum. So there is because energy, we are from lowest to highest if you arrange, and there is also related constructs like Fermi sphere and whatnot, that you study when we talk about the not semiconductor physics, when we talk about the materials. In that context that comes in. Okay.
Okay. Thank you.
Yeah. Okay. So where was I? Yeah. So this is the probability that any one of these energy states, any given energy state E, is occupied. So what will be the total number of, let's say, electrons? Electrons will be, so electrons can reside only in the conduction band. So I'll say integrate from EC to infinity density of states, that is the essentially the number of states that are there, times the probability that those are occupied, and we integrate it with respect to the energy. If we do that and we make some assumptions, we had obtained an expression something like this. This is for non-degenerate semiconductors, that is, they're not very heavily doped. Otherwise there are some other considerations that come into the picture. So this is the expression that comes. This is very similar to, in fact, what you see is the probability of the Fermi level. But anyways, for similarly for holes, you can find it will become I believe EF minus EV minus EF. Okay, right. So this is at equilibrium, that is, I'm not shining light, I'm not applying any bias, and this NC and the corresponding NV terms are known as the effective density of state. That is, you treat everything as not as the curvature. We're only interested in finding what is happening at near the bottom of the conduction band or top of the valence, because that is where the most fun things are happening. Okay, and finally, the best part of a semiconductor, as we had seen, is that you can dope them. That means you can change their conductivity. It's not fixed like a metal or insulator. If you dope it, let's say N type, this means it can give electrons. So electrons are residing here. We dope it, let's say in silicon we dope P type. The electrons can jump here. This is very small energy gap, so it can easily jump even at room temperature. On the other hand, there are other type of species which we call acceptors, whose level lies very close to valence band, and what can happen, electrons can now, which are in valence band, can simply jump to the this energy level. And this is the energy levels that we have explicitly created by doping. Okay, so and corresponding Fermi levels also change, but essentially now you can have electrons and holes available which can contribute to the current, right? And that's what we talk about here. How do they contribute to the current? You apply an external field, like we saw J equal to sigma E is the external field, or the counterpart you have must be familiar, V equal to IR, right? And so how so drift is essentially in presence of an electric field of any mobile charge carrier. So how do we see that? Vd equal to mu times external field E, and we saw it like the D is that this is the drift velocity at which the charge carrier is moving, and we saw it was something like this. So this is Vd versus electric field. In the linear region or the low field region, this is that. However, if you increase the field, it saturates, because now it starts getting scattered from your lattice from lattice atoms which are there, right? And then there is another transport mechanism, which is the diffusion, which is essentially happens to the concentration gradient. You have high doping of electrons on one side and low on another, so electrons will naturally flow from high to low. The corresponding coefficient is the diffusion coefficient, and they are related by this Einstein relation d by mu equal to kt by q. T is the temperature, K is a Boltzmann constant, and if, in fact, the change in carrier density, which will visit this concept today in today's session as well. So just a second. Yeah, so we saw that it's due to drift, diffusion, and generation can also happen, which we'll explicitly see today in terms of opto-electronic devices, and some recombination can also happen, right? And this was semiconductor physics. Then we formed our very first device, which is called the p-n junction, that is p semiconductor on one side and on another. So you have different dopings, and the depletion region will be formed because electrons will diffuse from one side to another. This is the depletion region. Orbit W arises due to the fact that there is no mobile charge carriers in that. Only the positively charged dopants are left behind, and negatively charged acceptors on the p side, right? P plus denotes essentially one side is p side is heavily doped. We saw how the charge profile looks like. The obviously, if there's charge separation, there will be an electric field. We saw the peak electric field at this point, which is also known as the metallurgical junction, and the depletion width that I talked about, where there are no mobile charge carriers. And if there is electric field, there will be potential, which we refer to as the built-in potential. Just for the sake of completion, this is how the band diagram of a p-n junction look like. So p and then in equilibrium. In equilibrium, this is how it looked like. So this is your EF. Fermi level is close to valence band, which should be P. Fermi level close to conduction band, which should be N. And this is where the bands are bending. This is the depletion region we have, right? But however, now we can also apply forward bias to that, which means is that the bending that you see, we reduce its extent. So essentially what we are doing is now we are connecting P to the positive terminal and to the negative terminal. We are injecting electrons and holes. So electrons will will be here, and then since this barrier is lowered, they can simply travel to the other side, right? And once they reach the P side, they'll recombine. And law of junctions law of mass action is Np equal to Ni square. Similarly, law of junctions is Np equal to Ni squared e to the power QVA over KT. Ni squared is, Ni is intrinsic concentration. Va is nothing but the applied potential that you have there. Similarly, reverse can happen in the sense that this bands will shift even more, and the depletion region will widen even. And an interesting thing can happen is that, and let's say an electron is here. Somehow it reaches there, and there's a very high electric field in the reverse when we are reverse biasing this diode. So in that case, what can happen is the electron will start to travel v square equal to u square plus 2. Let's say its initial velocity is 0. It has to travel a large distance. Remember, the electric field is also significantly high. It can obtain sufficiently high energy that this electron, which is traveling in the depletion region, mind you, can now knock out an electron from this atom. This electron can knock out another electron from this atom, and you can just see that an avalanche, a huge number of electrons will be released as you keep on progressing further and further, right? This is known as avalanche. Zener breakdown can happen is essentially just a band-to-band tunneling. So for instance, if I dope P and N very high, so the bands can look something like this. This is P side, this is N side. Now what can happen is that the tunneling can happen across this barrier. Okay, so this is what is referred to as the Zener breakdown. And we saw a few applications, particularly that for the sake of completion, the PN IV characteristics look something like this of a PN junction diode. This is the forward characteristics, and this is the reverse characteristic, and somewhere over here the breakdown will happen. Then we saw LEDs will come in the next session, photodetector and solar cell today. Tunnel diode we saw is a very, very peculiar device in the sense that it's again a P plus N plus junction in the sense that first the conduction happens to tunneling, then tunneling subsides, but the drift mechanism has not kicked in like this, and finally the drift mechanism eventually kicks in. So this is how it looks like. The peculiar thing is the negative resistance, what we call. Then we saw our second device, which we could know as Shockley device, is metal semiconductor junction. The related terms work function, electron affinity, and we saw two types of contacts are essential. So when I'm saying it's important, I'm making a wire being contact with a P-type semiconductor here. How does that happen? We don't want any funky things to be happening here. We just want the current to conduct from left to right and right to left, whatever the case may be. That's why we need a non-rectifying contact. Okay, and the mechanism here was thermionic. Okay, then we increase the complexity a bit. Now we have the three terminal devices, that is N, P, and N, emitter, base, and collector, right? And we saw the relative the dopings and width of emitter, base, and collector. How do we bias it? So we have two PN junctions, so we can have 2 into 2 4 combinations, and these are the 4 different modes that we have. We talked extensively about the working the forward active mode, that is when emitter base is forward bias and base collector is reverse bias. And we saw the emitter injection efficiency, essentially how many electrons are being injected across injected into the base across the forward bias junction. So let me forward bias it like this, and Pn is reverse bias, so Pn is reverse bias, something like this. So yeah, and then there'll be depletion region across the base collector junction, and if the base is narrow enough, very few electrons which are injected from emitter will recombine. Most of them will be swept away and in the collector, and that is what we refer to as the current gain, which is IC upon IB. There are other factors, base transport factor and efficiency. Then we came to a very important device, which was the bedrock of MOSFET, is MOSCAP. So we saw it can have two types, N type and P type. So essentially MOSCAP is essentially you have a metal, you have an oxide, and finally you have a semiconductor. Let's say P-type semiconductor. Okay, for P-type semiconductor you will have NMOS, and the various 4 regimes that we saw, that let's say you change the gate bias. So for instance, when you have negative gate bias, you can see the holes will be attracted to this interface. We call this accumulation. If you let's say apply positive potential, you will repel the holes and you will form a depletion region in this P-type semiconductor. If you keep on increasing it, what we arrive as something called the inversion. And this is peculiar in the sense that although this is a P-type substrate, what we have achieved is essentially at this interface, very close to the oxide semiconductor interface, we have an abundance of electrons. While the bulk stays p-type. This is an inversion of the characteristic of the semiconductor. It's peculiar things which can happen. This happened with the band bending and the potential at this interface. Okay, and then we saw various things like the threshold voltage is the voltage at which this inversion kicks in. So just to let me just draw a diagram over here. So this is let's say metal, and this is your oxide, right, and this is the Fermi level. So band bending will look something like this: EC, EF, and EV. So what you can see is that this is the metal side, this is the semiconductor side, and the bulk is still p-type. EF is closer to EV. However, at the sorry, this is EI, and EC will look something over here. However, at the interface, what you can see, EF is closer to EC, which is n-type. So this is what I'm talking about, the inversion of the nature of the semiconductor. Okay, and then we saw the capacitance voltage characteristic. That is essentially, since I'm saying this is a capacitor, so what you see is you vary the voltage that you apply, that vary the Vg, and see how the capacitance changes. So we saw that in accumulation, this capacitance will be exactly equal to the oxide capacitance, because everything charge modulation will be happening only across this oxide. This is the oxide layer, right? So however, if the depletion starts to happen, then you will have an oxide capacitance and depletion capacitance in series. So capacitance starts to drop. However, when the inversion starts, the inversion layer will also form over here. So that's what you see. So that is called the LFCV, low frequency CV. This is it. You are modulating the frequency voltage very slowly. So the charge electrons have time to come from the bulk and sit here and then go back. However, if you vary this very fast, that is change the voltage very fast, the electrons will not have sufficient time to come to the interface, and the capacitance stays flat, which is known as high frequency CV. So these are some characteristics that we see. Then we see some non-idealities, that is the metal and semiconductor work function need not be the same, so we need to apply some, and there's some charge traps. Again, these we need to apply some voltage which we call the flat band voltage, because that's where our analysis started. Then essentially MOSFET, so what you had this MOS cap, and what you essentially do is you add two more terminals. So on this side you add source, and the other side you add drain, right? This is the gate terminal, and this is the body or the substrate terminal. This you make it, and with this, for a p-type semiconductor, you make them n++. This n++ is essentially to make the non-rectifying contacts, as I denoted earlier. And as you can see from BJT, this is a 4-terminal device, and this is a unipolar device in the sense that either electrons or holes will be connecting the current, unlike the BJT where electrons and holes both had played a role. Okay, and again, so in the BJT, if you recall, the I had not drawn it, but IV characteristics used to look something like this, right? So we had, this is the cutoff region over here, and so this was the linear region, and there are other various regions in this, the current saturated. Similar thing, this is for a BJT. In fact, very similar picture happens for a MOSFET as well. Right, this is the linear region that we see, and finally the current saturated. This is again the output characteristics. So in the linear region and saturation region, we talked about this, we analyzed this using the gradual channel approximation. That is, the charge under the gate is due to combination of depletion charge as well as the inversion charge. So ultimately a point may so come that the channel becomes pinched off, and the current will not increase any further, right? And the substrate bias, the 4-terminal here, is not irrelevant. It's that you can just apply some bias to that, and you can see the PN characteristics of the whole device, of let's say of source and body will change, as well as of drain and body will change. So it's not that this thing is sitting idle. Yeah, it's not the body terminal is sitting idle here. It has a specific role which is used to tune the threshold voltages, for instance. Okay, in the last session we had talked about a different class of materials, semiconductors itself, but the compound ones. That is, till now we have been talking about, excuse me, just a second. Yeah, so we are talking about elemental semiconductors. We are talking about silicon for the most part. Compound semiconductors are there, for instance, gallium arsenide. It's a compound. It's made up of 2 elements. Another thing we saw was, let's say, aluminium gallium nitride, made up of 3. It's an alloy, right? Some 2,6 examples we see was cadmium telluride, right? 2D semiconductors which are there, like MOS2 we had talked about. And ternary means there are 3 elements like AlGaN. Quaternary means there are 4: indium, aluminium, gallium nitride. Obviously the complexity keeps on increasing. And then how do we obtain the band gap or lattice constant of them? We saw something called the Vegard's law, which we had seen is just that. So for instance, if it's ALX GA1 minus X, then the lattice constant for this would be X times the lattice constant of aluminium nitride plus 1 minus X times the lattice constant of gallium nitride. This is the Vegard's law. Same goes for the band gap, but band gap also had a slightly bowing factor. That is, the actual observed band gap was slightly lower. It had a bow in the plot. So for band gap, this should be the ideal one, but observed band gap was something like this. So this is the energy, and this is, let's say, mole fraction X. So this is, we are usually ignore the Boeing parameters for the for our analysis. And the key thing is that any material cannot be grown on top of any other material, right? And because the mismatch, they can be mismatched in lattice constant, and that can give rise to stress. And plus they have to belong to the same family in order to be grown on top of it. Gallium arsenide will not grow on top of aluminum gallium nitride, right? And this is the material growth part, and then we can form devices on that. Simply we can, heterostructure means joining two materials of different band gaps, like we saw p silicon nitride and silicon nitride to form a p-n junction. Similarly, we can I can form, let's say, p type aluminum gallium nitride with n type gallium nitride. So this is the heterostructure that we have. And with LEDs we can form a quantum well, which we had seen. And essentially it gave rise to 3 types of heterostructures. Just please refer to the lecture for more details. But the key terms is that, so the band is not continuous anymore. So that's what we saw. So for instance, if I'm just drawing just a second, I'm just drawing the bands as to how they looked, right? So let's say they look something like this. I'm not drawing the band bending as of yet, but they are there. So this is the conduction band, valence band. This is the delta EC, conduction band discontinuity. This is the delta EV, valence band discontinuity. And there are various parameters like the built-in potential, because if you include, which will be there, because Fermi levels need not be the same for both, for the left and right semiconductor, and thus there is a built-in potential, which I'm not talking it here, but it's there in the lectures. Okay, so for today's session, we'll talk about the optoelectronic devices. Okay, so as the name suggests, opto is light and electronics means some things to do with electrons. So somehow light and electrons are going to be interacting to each other, or cause and effect, whatever it is. Let's just see how they talk to each other. So we have been given some devices, and we have to answer some questions. So the 5 devices we are given are solar cells, a halogen bulb, LED, laser, and photodetector. So the question is, the devices which can convert light into electricity. So in fact, this is essentially the fundamental thing which is talked in what should I say, upper primary physics, 6 to 8 standard, let's say. Conversion, the energy can neither be created nor be destroyed, only its form can be changed, it remains conserved, so on and so forth. Same thing we are going to say here. So we have a light energy over here, and we want to convert it to electrical energy. Why do we want that? I don't know. There can be many applications, but light energy, let's say, is coming from sun. Okay, and electrical energy, let's say I want to drive a motor. Eventually, again, to drive a motor there'll be another step to let's say convert to mechanical energy, but I'm not talking about it. Let's say I just to provide a current to the motor, let's say. Okay, so which can convert light to electricity. So this means input has to be light and the output has to be electrical energy, some voltage, some current. So solar cells, I believe you must have seen it by now on in some fields, on top of metro stations, railway stations, sheds and whatnot, even if at your rooftops. Okay, solar cells essentially take sunlight and convert it to electrical energy, some current, some voltage. Solar cells do fit into the picture. So okay, this is correct. Halogen bulb is essentially which the street lamps that you see, the orange color street lamps, which are now most of them have been replaced with LED based light bulbs, but still some places you can find these halogen bulbs. So essentially what they take electrical energy and they convert into light energy. So this is the opposite of what is I've written here. So this is not correct. LEDs, light emitting diodes, as the name suggests, they emit light. right? So output is light, so this is also not correct. Lasers, again, you must have seen them. For instance, there are some light and music shows for entertainment purposes, for your presenting your while giving presentations, people use those laser pointers, right? So lasers are, again, light is the output, so this is also not correct. Photodetectors, as the name suggests, photodetectors, photon, they detect the photon, so the input is light, and you have to trust me on that, that output is electrical energy. We'll talk about them in today's session. Okay, so the devices convert light to electricity are solar cells and photodetectors. So 1 and 5, 1 and 5. Okay, okay. So how is that actually happening? So if you see, let me I hope you are able to see this diagram that is on the right. So you have the conduction balancement that is there. Okay, and we have, so what we can do is, if we shine some light, right, the electron can be now excited from the bottom of valence band to the top of the conduction band, essentially, but the light has to be at least the energy of the band gap. So this is what is showing optically generated electron hole pair formation. That's a technical term. Essentially, electron, you are just breaking the bond, and the electron will now jump to the conduction band, the hole is left behind, so electron hole pair is being generated. Okay, now we'll do the opposite now, which convert electricity to light. As I told, the halogen bulb is there, LEDs is there, we'll talk about in more detail in the next session. Lasers, as we have seen, is they have the laser pointers have a battery or some other electrical supply, and ultimately the output is a photon, a highly energetic or highly coherent photons which are generated in lasers. This is also a very interesting field. So as far as this problem is concerned, we have 2, 3 and 4 as the devices which convert electricity into light. 2, 3 and 4. So 2, 3 and 4, this is the correct option. Again, 1 and 5 we had seen, they convert light to electricity, solar cells and photodetectors, which will be the topic for today's session. Just a side note, this is not an exhaustive list. This is just which are either relevant to this course or which you have seen around. That's why these examples were taken, but there can be multiple examples. So for instance, I'll say okay, I'll ask this question. Name I should not say machine. Name any entity that converts light energy to chemical energy. You have to answer this while at this point of conversion of energy, light energy to chemical energy. Anyone? This just a hint, this will be in either 6th or 7th standard physics books or biology, science books essentially. PEC. Okay, what is a PEC? I'm sorry, I'm not aware. Go ahead, speak up. Photo
Electric cell.
Photoelectric cell. So photoelectric cell, if I recall correctly, is based on photoelectric effect. So a photon is coming, sufficient energy, it knocks out the electron from here, and now this electron can now contribute to the current. So if I understand it correctly, the input is light, right, and the output is electron. So isn't this a device which is light to electricity? I mean, yeah, you're correct, it's converting energy, light is the input, but I believe the output is an electron. An electron, if you make it flow through an external circuit, you will get current. So that's conversion of light to electricity. Light to chemical energy. This is, in fact, life as we know it will not survive because of it. It's the chlorophyll that you have in the plants. So chlorophyll, what it does is that, so it takes sunlight, and also like if I believe CO2 and there's one more material which I'm forgetting, and then it converts into this chlorophyll converts this light into chemical energy in terms of, let's say, sugars, glucose, fructose and whatnot, right? This is a chemical energy. These are chemicals. It's energy stored in frame of chemical bonds. This is a chemical energy. Ultimately we consume this. Herbivores consume this directly, carnivores consume the herbivores. So essentially that's how the food chain works. This is an example in nature. Light is being converted, light energy is being converted into chemical energy. Okay, I'll come to photodetectors. Our eyes are in fact one of the most efficient photodetectors that as humans we know. Again, they take light as the input, and ultimately behind in the eye there's an optic nerve. So the electrochemical signals are then carried to the brain. Okay, so there also energy conversion is happening. So this energy conversion happens all the time around us. It's just that only humans as a species, we have just tried to mimic some of them for our advantage. Okay, that's that. So someone mentioned photoelectric. We have photoelectric on your screens. So this question now talks about the solar cell works on the principle of dash action, and it works dash. Okay, so we need to talk about solar cell, and as the name suggests, it's a cell, so it contains something, I believe. Solar, something related to sun, a star. Okay, so do I have it? Yeah, I have it. So essentially solar cells, what we'll be talking about, the solar cell that we'll be talking about, they are essentially a p-n junction. Okay, we have already talked about this multiple times, p-n junction, depletion region, so on and so forth. Let's just forget about this external circuitry for now. Okay, so a very simple thing, this is a p-n junction, right, and there's a depletion region, it's in equilibrium, right? So it's band diagram. I also draw the band diagram, so it will look something like this. Okay, so this good fellow is just sitting at equilibrium. EF, we have EC and EV, right? And mind you, this is the depletion region, right? And so this is the negative side. I'm not drawing too many of them. These are the lattice, the dopants or the acceptors, whatever you may call, on both the sides. Okay, and consequently, as we had talked about, at the metallurgical junction, right, there will be an electric field only in the depletion region. Okay, I'm just drawing this symmetric, but this is just for illustrative purposes, electric field with respect to x. Okay, let's say now, although the depletion region, we say that it's devoid of any mobile charge carrier, so all the electrons and holes which are there, they have moved away, and thus we are left with this sort of a static system, so to speak, of just the fixed ions, right? And it's not connected to any external battery, any external voltage source. Now let's do, I shine light. Okay, so this is what is depicted over here. So let me shine some light. Let's shine some violet light on this. What's going to happen? Now the question that arises, is this light sufficient enough? Now see, it cannot do much in this depletion region, but it can do, however, if there are some electrons which are in the valence band over here, right? It can provide sufficient energy that these can jump to the valence band. This process will happen here also, no doubt about it. It does happen over here. That's why we have to design it carefully. But let's just say, if an electron in the valence band, if its energy is high enough, and I'll assume that h nu is greater than or equal to Eg, the band gap of this material. So this electron now here will jump to this, right, and will leave behind a hole. Now what we have done, we have generated an electron hole pair. This is the generation of electron hole pair due to a photon. Okay, what does this electron hole pair do? These are mobile charged particles. Please understand, we already have an electric field that exists over here. Okay, so what's going to happen is, which I'm going to denote in green color, is the electron now will move, right? Electric field is a negative x direction, so electron will move in the positive x direction. Okay, and the hole will move in this direction. Now we have a drift of electrons and holes. This will give rise to a current. Essentially, this is the current that I am talking about. So the current's direction is from, this is the direction of current, which I call this I light, let's say. That is, this current is arising only due to the presence of light, and of course the circuit is complete. The circuit has to be complete. And in the external circuit, I am driving a load. Let's say I'm charging my phone, or I'm running a fan. Very straightforward things. Okay, so this is what is happening, and so the current can flow, right? But there are two conditions, as I told you. primary two condition, H nu must be greater than equal to Eg, and there must be an electric field that must be present. That's why I say if it's happening here, there's no electric field in the quasi-neutral region. So even though photons are falling here, it's of no use to us practically. Okay. So what we notice is that let's now come back to this problem. I've just introduced the very basic functionality, how it functions. So what we see, solar cell works on the principle of photovoltaic. Okay, photoelectric, as someone had pointed out, photoelectric essentially is when a photon is falling on a material, and this electron is physically knocked out of the material. So that is a difference. Here the electrons is just jumping the energy states. So think of it like this: you're sitting in a class and you come from, let's say, from the last bench to the front bench. You are not leaving the classroom. That's photovoltaic effect. Okay, that's just the photovoltaic effect. Photoelectric will be you leave the building altogether. That's photo. Or let's say you're sitting in a classroom on the first floor and you go to the fourth floor. That is the excitation. Okay, and you move on the fourth floor, you move from one room to the other room. That is essentially your transport of the electron in the conduction band on the fourth floor itself. If you leave the building altogether, you leave the building in which on the 4 floors which are there, that is photoelectric effect. This is not the operating principle of solar cell. There are devices, but not for solar cell. So solar cell works on the photovoltaic principle. So this. And as we notice, it does not need any external electrical supply. A load is there, you can supply it, but it does not necessarily need, and otherwise it would be useless. So for instance, if you're asking people to adopt solar cell on their rooftops or on their workshops and whatnot, right? It doesn't make sense to supply the battery to supply power to in order to run it. They'll say, okay, why do we need it in the first place? So that's why you ordinarily do not need any supply. Okay, so photovoltaic and without a supply, so this will be the correct option. Okay, please note that photoelectric is different. There are applications, but solar cell does not work on that. Okay, and the key principle is the generation of electron hole pair and the traveling of those electrons and holes as per the electric field which is present. Okay, now as I told that solar cell essentially works on the input energy is light, which is coming from sun. Okay, all right, so now we have to understand sun how. So we know that as the evening approaches, like now the time is around 3:30 or 4, so the sunlight, the power that is going to be generated will be lower because it's evening, and plus you can see it's slightly less warmer to go out right now as compared to, let's say, 12 noon or 1 p.m. Okay, so what is happening? So that you can easily understand is something like this, that this is the Earth's surface. Okay, and we have sun somewhere over here, right? And I'm drawing this at exactly 12 noon, so this means sun is directly overhead. And let's also draw the Earth's atmosphere. So extending up to a few kilometers above the surface of the Earth. Okay, hugging the curvature. So this is our Earth and this is the atmosphere. And let's say what's happening at exactly 12 noon. Okay, so 12 noon, let me draw it with violet. So at 12 noon, the sunlight will have a direct, will have to travel the least distance in the atmosphere. Why is that important? Because in atmosphere we have various gases, first of all, oxygen, nitrogen, carbon dioxide, argon, so on and so forth, and water vapors and clouds. So clouds is essentially where your water vapors have condensed into form a droplet or an ice crystal, and essentially they coalesce around some impurity, which is usually dust or dirt, and some other, there may be other pollutants also, right? And plus there is, as you come to the lower reaches of the atmosphere that is closer to the surface, you will find higher dust pollution, some other pollutants like particulate pollution will be really high, especially in cities and industrial areas. So all those local factors do play a picture, but essentially sunlight will have to travel this straight distance, right? And this distance will be minimum when it's at directly overhead. Okay, and there's one more interesting thing that happens is outside the at this point, just outside the atmosphere, the sunlight will essentially be I mean, there's nothing to scatter it as it's traveling from the sun, and it travels millions of kilometers to reach just the periphery of the earth's atmosphere, and it will be like nothing is lost here. Okay, something will be lost in the as it reaches the atmosphere. Okay, all right. So let's draw one more picture. Now let's say we are talking about 3 p.m. So this is 3 p.m. Okay, and again I have to reach the same point. My solar panel is sitting over there. Again, let's talk about 2 points. The point which is just outside the earth's atmosphere, that thing, and the other is where my solar panel is placed, that is just at the surface of the earth, right? So as you can clearly see, the green light, right, has to travel more distance in the atmosphere, and consequently it will be scattered more, right? So there are few terms that are associated, because when we want to fabricate these devices and deploy them in the field, we need to know how much sunlight is coming. So there are few terms that have been associated with that. And as you so this is just so in the yellow, or in the red line that you see over here, in the black line that you see over here, is the sunlight without any atmospheric absorption. So this line that you're seeing, okay, there's no absorption is there. So this is this point I'm talking about, this point and this point. This will be the same whatever be the time of the day. It's earth that is rotating, but sun's light will be reaching this part unless it's behind it. Okay, we're assuming it's still daytime. Okay, and sunlight is composed of various wavelengths starting from 250 nanometers all the way up to 2.5 microns. What we have on the y-axis, essentially what you can see is the power per unit area, watt per meter square. So if I'm deploying a solar panel over here, it will have a given area. So we normalize with respect to area, and per nanometer, that is, if we integrate this whole area under the curve, you will get power per unit area, which is of importance to us. Okay, so so this point, which is just out of the Earth atmosphere, which is known as AM0, air mass 0. Okay, and which is coming the sunlight, the power associated with that let's say which is coming directly is AM1. Okay, this fellow is AM1. So what you see over here is this orange thing that you are seeing is, let's say, is AM1. Okay, and as you can clearly see, between yellow and orange, there's significant absorption, right? Where is it being? And you can also see some dips. So for instance, this dip that you are seeing here is due to oxygen, here it's due to water vapor. So there are multiple absorptions due to water vapors, you can see, and here is CO2 around 2 microns. So essentially there are some sunlight which is coming on the surface of the earth is being absorbed. Okay, right, and that is the path length. So when it's direct overhead, we call this AM1, that is the least part that it can have. This is the reference. Now let's say when you are at 3 p.m. okay, you must be traveling, let's say 1.5, I don't know what the number is, but these can be calculated. Let's say this is AM 1.5. The question says is that at 4:30 p.m. so we are now gone even further, right? So let me draw in not red but orange. Okay, so at 4:30 p.m. we are over here, and again the light has to follow this solar panel. So this is 4:30 p.m. and it's AM2. AM2 essentially means twice the length in the atmosphere. So orange ray of light travels twice the length in the Earth's atmosphere as the violet ray of light. That's what it means. Okay, how this is abbreviated as, that's what we have been talking about. This will be abbreviated as AM2. The path length is twice, and the intensity with respect to AM0, as you can see, because more of it will be now absorbed in the atmosphere, dispersed and so not, so the intensity will definitely be lesser. So this is the correct option. AM2 denotes the path length with respect to the minimum length which happens at 12 noon, and the intensity will naturally be lesser. This is what we actually feel, lesser. You feel lesser standing under the sun, especially in summer months in northern India. You'll feel that it's much less forgiving, it's much more forgiving at, let's say, 4 p.m. or 5 p.m. as compared to 1 p.m. That's essentially what is happening. Lesser intensity, you feel lesser heat, and eventually solar panels will also feel lower amount of photons reaching them in the evening or early in the morning, whatever the case may be. Okay, that's how this air mass is related to that. And the second thing which I wanted to note is that the sunlight comprises of visible naturally and also infrared and UV, but there's not much UV is there, but still this UV is significant enough to cause some problems, especially at high altitudes. Okay, right, that's okay. Now I need to make some solar panels. So which material should I pick? Okay, we know it should be a semiconductor, but as you can suggest that, so which material should I pick so that the light should be sufficient? Please remember the same thing, H nu should be greater than equal to Eg, right? So I should pick, let's say, material with this much of wavelength, let's say lambda equal to 2.5 micron. If I put lambda equal to 2.5 micron, now its energy, so correspondingly all these energies, all this, because its band gap will be corresponding to this. And if you recall that expression which I talked about earlier, 1.2 divided by lambda in micrometers, that gives you Eg, right? So corresponding 2.5 microns, right, 2.5 microns is, let's say, 0.5 eV, let's say. So any material which has at least 0.5 eV band gap, it will absorb all of these wavelengths. All of the solar spectra can now give rise to photons, the photovoltaic effect, and thus we can have a huge amount of current that is flowing. It appears that this would work best, but we'll see as we move forward. This does not always work the best, but essentially what you can see is that, so let's say I choose silicon as my material. Okay, so let me choose silicon. Let's say where the silicon lie here. So silicon, the band gap is 1.1 eV, right? And correspondingly the wavelength will now come out to be the lambda corresponding to will simply be 1.2 divided by 1.1. So let's say it's coming out to be 1.1 microns. Okay, so 1.1 microns, this means somewhere over here. So this is silicon, lambda silicon. So below this, silicon will absorb everything, can absorb everything rather. It will depend on various factors, but silicon based solar panel can give at least electron hole pair in all these wavelengths. All these wavelengths will be naturally wasted. Okay, let's say if you want to try germanium, forgetting what's for germanium. Gallium arsenide I know is 1.4 eV, so let's try gallium arsenide. Gallium arsenide is 1.4 eV, so lambda corresponding to gallium arsenide will be this will be 1.2 divided by 1.4, it will be 8.86 microns, 0.86 microns. So that will lie somewhere over here. This one for gallium arsenide. Gallium arsenide will absorb all this, but it will not absorb above it. So that's the trade-off that we have to make. We'll see which one works better. Okay, now let's talk about the design of the solar cell. So we know this is basically how it operates. You have to shine some light and whatnot, but as I was telling is that if the light falls on P or N regions, it's of no use to us, right? Because there is no electric field to make these electrons and holes travel in order to complete the circuit. So first thing which we notice is that we should try to make the photons fall as much on the depletion region as possible. So one way to do is that you just reduce the thickness of P side. So let me just draw the very first design. So this is your P, and remember again these are epitaxially grown, so this is my direction of growth. Okay, so that part always remains, please remember that. So this is the direction of growth. So this is my n-type material, this is my p-type material, and there will be some depletion region, right, and there I will have one terminal, correct, this terminal 1, this one, and this side we have terminal 2, and let's say this is the terminal 2, and here I can hook up the external circuit. Fair enough. Now please understand, the photons are falling from the top. Where are they falling? They're falling on the quasi-neutral region, which is of no use to us. So actually it's not that they'll be absorbed, some of them will be absorbed, but they'll travel to this depletion region eventually. So what makes sense? It makes sense that we make the p region as thin as possible. Okay, so let's do that. In my second generation of design, what I do is I make the p region as thin as possible. So n region remains the same, right, and I have thinned down the p region. And again, these are your two terminals, 1 and 2, which will be connected to the external source. All right, what usually happens is that you also need to make this contact. So if you have thinned that, its resistance increases, and thus even you are producing electrons will not be transported out efficiently. That's why we need to dope this high, p plus type. Okay, then it works. Even if it's thin, the resistance is good enough that this contact is a non-rectifying contact, works properly. So this is a p plus, and when we have p plus, now you know, and this is n, so depletion region will be extending into the n side. This is very less will be in the p region. So this is how your design will essentially look: p plus and an n, and your depletion region is extending naturally into the n side. Now let's now understand again. So some photons are falling over here again. Some of them, yes, will be absorbed here because due in this material itself. But if we choose it carefully, if we choose the thickness, if we make it thinner, then a heavy majority of them can reach the depletion region, and there they can generate the electron hole pairs. As we know, the electrons will jump from here to here, leaving behind a hole, an electron here, and the electrons can now and hole thus can travel. And this external circuitry you can complete, you can apply a load over here just to complete the whole circuitry. So this is how it's actually done. There are various things like it has, in a solar panel you have to apply some protective cladding to prevent it from, to mitigate the effects of let's say dust and other pollen grains and whatnot, and these supporting structures, all those things come into the picture. But the heart of a solar cell is the p-n junction, and that's how we make it. So we dope p slightly positive, n is, let's say, moderate doping, so the depletion region extends in this side, and only in this p is thin enough. So that's how, and with this configuration, now we can operate this solar cell to a reasonable degree. All right, let me see if there is anything else that I'm missing. No. So material I have already talked about. The material that as we see in this slide, you can choose silicon, gallium arsenide, or let's say some material with band gap of 0.5 eV. Let's say it will work wonders. Will it work or not? At least theoretically it looks like it works for now, but we'll see what material is best suited for that. Okay, so this is how a solar cell is primarily, p-n junction is the design, how it looks like. Okay, now let me talk about a bit about the operation. Okay, so in the first I think second or third slide, I mentioned that it works on photovoltaic principle. That is, it does not need any battery to operate. Okay,
so you're told p plus.
Yes.
So majority carriers are holes.
In p side, yes. So but when the electron hole pair is generated, right, so that's what I was coming to. So in p side, complete your argument.
So light is falling on the p plus side.
It is falling on the p plus side. So it is falling, let's say, let me just draw it over here, how it will look like, the way we are habitual of seeing it. So this is the metallurgical junction, this is the p plus side, and this will be the depletion region. Yeah, go ahead now. So light is falling from this side, right? That's what. Now I'm just showing a different cross section. Yeah.
Then majority carriers are holes.
No. See, light does not have any carrier, so to speak. Light is just a photon is just a packet of energy here. In this region, yes, there are majority holes, but this is a neutral region anyways, right? This region, however number of holes are there are number of correspondingly for every hole there is a corresponding Na minus. So this region is electrically neutral. I'm not applying any external battery or so. In this region, yes, but what's the point that you're going to make? I'm interested in hearing that. Go ahead.
Yes, yes, sir. Understood.
No. Please complete your question. Now I'm more intrigued.
So as soon as the packet of energy comes in, it creates or generates the electron from the bonding.
Yes, it will generate here also. Yes, correct. But that is of no particular use to me, right? It will generate and it will recombine itself here. So it may recombine sometimes. That's why I'm making this thin. I don't want. So essentially, what happens is that. So I should tell you one more concept rather. So let's say a light of intensity I naught is falling here, and let's say that the transmitted is IT, okay, and this for any given frequency of wavelength that is falling. So this is a light photons, a ray of photons is coming here. So essentially I can write IT over I naught is e to the power minus alpha times T or D, let's say. This D is the thickness. So light is falling on the left side of intensity I naught. It passes through this material of thickness D, and the absorption coefficient of this material is alpha, corresponding to that given frequency for which this light we are talking about. So you can see that the transmitted light will naturally be of a smaller intensity. Intensity essentially means number of photons. So there will be smaller number of photons. So that's what I'm saying. If I make this very thick P plus region, then this number increases, and thus less of the light will reach at the depletion region. That's why I want to make D smaller. You can argue that okay, choose a material which has smaller alpha. Absolutely, that will work. But in the nature we are limited with we need a semiconducting material of a reasonably low alpha, right? And we also want to reduce the thickness T so that the intensity that is reaching. So here starts your depletion region. This is the depletion region. Okay, here IT is reaching here. This is the depletion region. So what you want is that, I'll write it here again, IT over I naught is e to the power minus alpha D. So you want IT to be as high as possible, because the electron hole pair which are of interest to us will be generated only in the depletion region, right? So we want alpha and D. Alpha, let's say we cannot control to a certain extent. D is under our control because we are growing that material, right? That's why I need D to be smaller. Even some will fall here, yes, definitely. Electron hole pair will be generated because that's what this alpha denotes, right? But what I'm more interested in, what's reaching the depletion layer. Okay, that is, I should have. Thank you for pointing this out, because this point otherwise I would have missed. All right. So we have designed it now. Now let's see how it operates. Okay. So as I've said that it operates without any external power supply, so to say. Okay. So let me just a second. Okay. So what we'll do is this is a PN junction. And on the dotted line that you see is this is your typical PN junction diode. Fine. Reverse side is not shown, but let's just say it's here. This is here. Forget about the breakdown, this problem. Okay. So what is going to happen is that when I'm not shining any light, this PN junction diode will behave exactly as to this PN diode that I have written. The forward bias, this is the characteristic, drift diffusion, whatever you have, and on the reverse side is some reverse saturation current that is flowing. Now let's see what happens when I shine some light. Okay, that's where the interesting things will start to come into the picture. Now again, I'm interested in writing only at what is happening inside the depletion region, because again, whatever is happening here is a quasi-neutral region. It's of no particular significance to us. Yes, it will be absorbed, it will be created, but then it will be recombined within a diffusion length. So not much fun things are happening here. Here there might be. Okay, what I'm interested in finding out, what is the excess number of holes that are generated. So now I'm considering p plus n junction. Okay, so from this analysis onwards, it's a p plus n junction. So in the p plus n junction, we only talk about holes. Why? Because the concentration is so much large that they are going to dominate the mechanism over here. We'll see that. We'll generalize this a bit more, but let's just focus on holes for now. Okay, so what's happening? So let's say, as I told, the continuity equation that we had that I had briefly alluded to in my opening remarks. So what we have here is that what is the excess? So we'll write that expression. Okay, so we'll write that del square delta p over del x square, this comes from diffusion, right, minus delta p is excess holes over tau, their lifetime in which they recombine, plus optical generation rate. This has to be in steady state, this has to be the case. And in which region I'm writing this expression? I'm writing this in quasi-neutral region of n. On this side, I'm writing this expression. What is happening? When the light is falling here, electron hole pair are being generated. Okay, and you know electric field. So this is let's say this will be the negative side over here. This is the positive side over here. Okay, right. So what's going to happen is that there will be excess holes which will be present here. Again, I'm just assuming that I'm not applying any drift. That's why I don't see any drift component. So this is the diffusion. Second. Okay. This is the recombination. This is the generation. Okay, so this with the appropriate, I'm not going to solve this here. I just wrote this. It's just to illustrate there's a physics behind this that is dictating this. Okay, and how does the delta p even look like? I can draw that at least. So let's say this is Wn over here. Okay, this is Wn. This is 0. This is 0. And I'm drawing the concentration of delta p. So, and this is the background. The background would be p and 0. The holes on n side, 0 means equilibrium. So this will be nothing but ni squared over nd. The whole concentration on this side. Excess holes profiles will look something like this. This is the excess holes that I'm talking about, delta p on the n side. So this is the diffusion, because they're excess holes. Where they came from? How did they appear here? They appeared because we are shining light, as simple as that. That's the reason they are here. When they reach here, they'll recombine. They'll have some specific time, lifetime. And then we have the optical generation that is happening. Okay, if we try to solve this, essentially this expression with appropriate boundary conditions, what we get is that the total current, I have it here. No, I don't have it here. Sorry. So I have to write this. So the total current will be, let's say, IPN, the pure PN junction, and I light. The effect of PN as well as light. What is the current due to PN? We know the reverse saturation current, exponential VA by KT, QVA by KT minus 1. This is your VA is the applied potential. Now I'm generalizing in the sense I have also applied drift. So this will be flowing in some direction. How? From P to N, correct? But as we know, the light current flows in the opposite direction. We have already talked about the holes will travel from right to left, which are generated here due to light. Okay, what will be there? it will be Q times GOP, the optical generation rate. This is per centimeter cube per second. So we have to apply it with your volume. So volume is area times the what we have here is just the diffusion length of holes. Why? Because actually it will be a more complex. It will be W also has to travel this depletion length and whatnot. So I'll generalize it a bit more. So I'm just ignoring also the depletion width over. Usually the diffusion lengths are much larger than depletion length. So this is a more realistic picture. That's how it comes to look like this. The key thing is that it's made up of two components, right? The PN, which you see this first line over here in the IV characteristic, and secondly it's shifted on the negative when we shine light. So you see this shift. This is due to light. That's what I want to highlight. The shift that you see is due to light, and because some electron hole pairs are being generated and they are traveling across the depletion region and being collected somewhere or the other. Okay, hence this whole curve shifts a bit down towards the right. That's the whole point of it. Okay, now some key things that we can really relate to is that, so even if you don't apply any bias, that is V equal to 0, some current is flowing. What will be that current? That current will be exclusively due to light, because if you put VA equal to 0, this first term to the PN junction comes out to be 0. E to the power 0 is 1, 1 minus 1 is 0. So all the current that you're seeing is just due to shining of light. Sometimes this ISC or short circuit, also known as the photocurrent. Okay. Second thing you notice is that in this expression, if I put current equal to 0 means essentially remove any load. You make this open circuit. So when we make this open circuit, what's going to happen is you put I equal to 0, and you can obtain this expression. We know everything. We can find what the value of VOC is. So this is IPH or ISC, what we call. It will be ISC upon IS, and you can take the logarithmic. I have the expression in the next slide, don't worry about it. But this is again a key parameter, VOC. Now, the thing is, it's typically said that we operate solar cell in the fourth quadrant, and I've told you, you need not apply any bias to get a current. That is true. But usually what is done is that some small bias is applied. Okay. Another thing which you associate with solar cell is the self bias. That is, it is biasing itself. How is it happening? So you see, if you shine some light, right? If you shine, this is the diagram. I'm shining some light, and some current will be flowing in the direction that is shown here, right? And you see is that P plus is essentially at a positive terminal because current is flowing like this. So if you put V equal to IR, I'm going to use a different color. If I try to evaluate this V equal to IR, this will be positive, right? When you're shining some light. This and please note that I'm not applying any bias, so I'm operating essentially at this point. And so what is that? Essentially, this PN junction diode is forward biased. That's why it's called self bias. Itself is driving into a forward bias mode, so it operates somewhere. If you apply very high bias, let's say 5 volts or something, you're essentially going into the first quadrant. So there you lose all the peculiarity of the light, because there IP and this exponential term will significantly start to dominate whatever this optical generated, whatever this current due to this photons is. That's why we restrict ourselves to the fourth quadrant. The self bias, I hope I have explained. And now we have various, so this was the circuit diagram and the IV characteristics, and there are a few expressions. So this is what I have written. The total current, the first component that is coming is due to the bias that you are applying. Okay, and negative sign denotes it's in the opposite direction, because for PN junction, current flows from P to N in forward bias, while when you're shining light without any bias, the current will flow from N to P, because due to the electric field that is present there. Okay, right, and this is the component. So here I am not talking about a PN junction, P plus N, rather anything which is there, any generic PN junction. W is your depletion width, LP and L are a diffusion lengths. Okay, and the short circuit current, as you can clearly see, if I put VA equal to 0, Okay, there's a -1 that is missing here. Sorry about this. It's QVA KT -1. Okay, if you put VA equal to 0, this first term vanishes, and the current that you obtain is only this. So that is the short circuit current. Where does the VOC come into the picture? That we can derive now. VOC, we put this I equal to 0. Okay, for VOC, put I equal to 0. So if you put I equal to 0, it will be IS e to the power Q VOC by KT -1 equal to ISC. This value is nothing but ISC, this on the right. So from this I can get ISC by IS plus 1 equal to e to the power Q VOC by KT. Take logarithmic, so you get VOC equal to KT by Q natural log of 1 plus ISC over IS, which is the expression here. IL is nothing but the current due to light. So these are various forms. I light is I photo current or I short circuit, essentially means the same thing. Okay, there's one more component which we call the fill factor. So essentially the regimes, the maximum current that you can have is this ISC, the maximum voltage you can have is VOC. So you see you can essentially form a triangle, a rectangle over here. I'll try to draw this. This rectangle. Right. Fill factor is essentially where you're operating versus the maximum limits that are available to you. So essentially it would have been the best if this were a perfect rectangle, if this curve would have completely coincided with this vertical and horizontal line. That's not going to happen. So the closer we are to this perfect rectangle, the better we are in the operation of this solar cell. So these are various terms or expressions that you will come across. Okay, so now let's based on our understanding till now, we'll try to solve a few problems of solar cells. So this is an analytical problem. So we are required to consider two solar cells. Solar cell A is P plus N and B is N plus P. So again that the depletion is on the one side, and the geometry of the device, that is thickness of P plus region in A and N plus region in B, are equal and it is thin. So this is the efficient design that we had talked about, and the thicknesses of N and P region are respectively equal. The dopings are also the same. Okay, and they are made up of both the same material. Okay, so what I'll do is, okay, so I'm just first drawing solar cell A, how it looks like. Solar cell A is P plus N. Okay, so we have P plus and N, this is A. Okay, and on the other hand we have B, so then we have solar cell B. This is N plus and P. So this is solar cell B, and but the thicknesses are the same. So whatever, so essentially geometry is not going to play a role. In fact, that's what it says. And doping for P plus is the doping in N plus here. So all those terms are also not going to play a role. And they are the same material. So let's say silicon or whatever the material is. So the band gap is also the same. Which of the solar cell operates better? So better, the only term that we have come across of the so-called better is the I short circuit, and the second thing that we have is V open circuit, right? Higher those values, the better off we are, and essentially the more room you have to play. Okay, so let's just talk about I short circuit over here. Again, this expression, there is a -1. I'll correct this when I'll upload in the in my notes. Okay, so what we have is now let's just try to compare ISC for these two fellows. Okay, so the thing that is going to be different VA, I'll assume applied bias is the same for both of them. Okay, so let's just first say what ISC is going to be. Okay, so ISC for this will be QA GOP and LN. Why LN? Because the electrons are the one that are going to diffuse in the p side, and we need to consider that. Okay, and for the other solar cell 1, it will be ISC A equal to QA GOP LP. Now GOP is the optical generation rate, that will depend on the material, which is the same in both the cases, as well as on the let's say essentially what time, what solar spectra. Again, we'll assume the same for both of them, and the geometry is also the same. So the only thing that's going to differ is the diffusion lengths. And typically what we have is ln is greater than lp. This implies ISC for B will be greater than ISC for A. Okay, so we have now completed the first analysis. Now let's do the analysis for the open circuit. For that I'll need, yeah, just a second, I'll need that expression KT by Q. Okay, so VOC, first I'll write it here so that it's, okay, let's do this, KT over Q 1 plus I photocurrent by IS. That is the expression, right? IS is a reverse saturation current. Okay, so KT by Q will be the same for both of these. Photocurrent is, as we have seen, will be slightly higher for the solar cell B, because ln is greater than np. That's what we have established just now. Let's talk about this reverse saturation current for a minute. Ni squared will be the same for both, right? So this is same for both. Ni squared is same for both, right? For this red, for solar cell A, what is going to dominate is this other term, because Na is like much higher, so this will be neglected. So for this, Is will be dP over Lp times Nd. Okay, and similarly for over here, for let's say ISB, this will be dN over ln times Na. Again, Na and Nd are the same, so that terms also vanishes. The only thing it depends on is the respective ratios of dP over Lp, and in this case dN over ln. So what happens is that they tend to be, I mean, they are different, but the ratio is that dP is also higher for, sorry, dN is also higher and ln is also higher. So the ratios are more or less going to be come out the same. Okay, what I mean to say, the reverse saturation current will not differ by that much, but their photocurrents do differ. Okay, and the photocurrent is higher for VOC, so this will establish for me that let's say ISA is approximately equal to ISP. Okay, if we assume that, then it's only the I photocurrent of B, since it's greater than A, so which is good. This implies VOC of B will be greater than VOC of A. The numbers, actual numbers, we have to put in. I do not have those numbers readily available for me, but that's the way to approach the problem. That's what I'm saying. Okay, so we see that solar cell B is better, as simple as that. Moral of the story. Okay, we put in the actual numbers, we can find out the how to what extent it's different, but prima facie it looks like solar cell B will operate better than solar cell A. On the other hand, the other way to say is that N plus P device works better due to their higher diffusion lengths. Simple as that.
Both the parameters should be maximum. Yes, that's what.
Yes. The higher they are, the better essentially you are operating, because
that is maintaining that rectangle.
Yes. Okay. So now another problem where we have to compare two solar cells. So this time solar cell A and B, they have the same geometry, same doping, same type, thickness, whatnot, and A is made of germanium. Okay, so let's do this again. P plus N made up of germanium, and solar cell B, this is A, and then we have solar cell B, again P plus N. The dopings both sides are the same. This is silicon, no sorry, not silicon, gallium nitride, and this is B. Okay, now again we have to compare the short circuit current, and secondly the open circuit voltage. Okay, so the key thing, as you can see, is that the primary thing that is different is the material, the semiconductor material that we have. For that we need the band gap of germanium, which I believe is, silicon is 1.1, gallium arsenide is 1.4, I think it's 0.7. okay, so this I know is 3.4 eV, and for germanium it's going to be 0.7 eV. okay, let's just try to find out first of all what will be the your short circuit current. Okay, the short circuit current is essentially when you're shining light. How it depends on how much frequencies can you absorb, can this device for instance absorb. So for 0.7 eV, let's convert this fellow to our energy, to our wavelength. So a wavelength in micrometers, I'm just choosing the 1.2 over Eg. Okay, so this is going to be, let me just get my calculator, 1.2 divided by 0.7. so this is coming out to be around 1.7 microns. okay, so let's say I'm drawing this here. So this will be my germanium. Germanium will absorb everything over here. This will be absorbed. Okay, second we have is gallium nitride. So gallium nitride, again correspondingly lambda will come out to be 1.2 over 3.4, so that is 355, so 0.35, let's say, micrometers. 0.35 micrometers will be somewhere over, very coinciding to UV and visible. Okay, so let's just say this is gallium nitride, and only these will be absorbed. Again, I am ignoring the absorption coefficient and everything. It's just to say that at any given point of time, let's say we are operating at AM1, right, which means this orange line and this orange curve that you see of the solar spectra. So gallium nitride based device will be absorbing very few of the wavelengths, right, and thus it will be generating very small short circuit current. Simple as that. The GOP term that we had seen, right, is optical generation. It depends on, it was not, I did not say it explicitly, essentially that how much of photons, electron hole pairs, are being generated. So if you have very few wavelengths, very few intensity, or very few number of photons available, naturally GOP will decrease. So for gallium nitride, the short circuit current will be definitely smaller. Okay, so for solar cell, we can see short circuit current will be smaller. Let me write it. What I can say is that ISC for A will be larger than ISC for B. Okay, short circuit current has higher short circuit current as compared to B. Fine. Now let's talk about the open circuit voltage. Now open circuit voltage is again very simple to understand, in the sense that this is the open circuit voltage, right, and what it depends is, you can see again the doping and all, again it will depend on diffusion constants or not. I don't know what their numbers are, but they're usually in the same ballpark, and they're not wildly different, right. Ni is a number which is usually very different. Okay, so and how do I know that? I've talked about it explicitly multiple times, that you must remember to first order Ni square is this, is inversely dependent on the band gap. So when we have band gap of gallium nitride is 3.4 eV, exponential dependence, mind you, and yeah, so what this would mean is that Is for gallium nitride will be much smaller than the reverse saturation current for germanium. This term is smaller. This would mean that open circuit voltage for gallium nitride will be much, because there's a log, so I'm removing the much larger term here, will be VOC of germanium. Okay, so open circuit voltage for gallium nitride based solar cell in our problem here will be larger than the open circuit voltage for germanium. So solar cell B has higher open circuit voltage as compared to solar cell A, and this is the typical trade-off that you see. I told you need a high ISC, and high VOC for for a better performance. There's a trade-off. If here I'm just comparing the two materials itself, but this is a fundamental trade-off that we have observed. This is the Shockley Queisser limit. Okay, on the chart on your screens, on the left side, y-axis is the efficiency, and the x-axis is the material or band gap, if you want to call it that. Okay, and this is for different material systems. Of germanium, for instance, we had just obtained, right? How do we obtain the efficiency? I should point this out. It essentially depends on VOC times ISC. This is a critical parameter. There are some input terms also. Let's not worry about them, but this is the term which we had talked about. So VOC and ISC, that their product, the power essentially, right? It depends on that. So you can see that it peaks at around 1.5 EV or something. Okay, which happens to be very close to gallium arsenide or cadmium telluride, these two semiconductors. So you can see that solar cells, for these will be more efficient. However, silicon is not far behind, which you can see. This is the theoretical limits, by the way. Okay, and you can see that silicon is operating somewhere at around 32-33%. This more or less flat lines here. And since silicon is much cheaper, right? So you can see some silicon based solar panels which are there commercially available. For some specific applications, yes, you can use them for silicon, germanium, and whatnot. But I'm talking about the commercial solar panels that you see. This is the fundamental trade-off essential that I wanted to talk about. For more details, please refer to the video lectures of Professor Digvijay. He has explained in much more detail. I am just passing in reference. Okay. Now a few more problems, and then we'll wrap up the section on solar cell. So this is, consider a silicon PN junction solar cell with this much photocurrent and this much reverse saturation current at room temperature. Find the open circuit voltage. So in this problem, for instance, it does not talk about it. It does not mention, for instance, let's say it's a P plus N junction, N plus P junction. So whenever such kind of whenever you encounter such kind of problems, please always just bear in mind to ask yourself these questions, whether this is the, it says it's a silicon solar cell, silicon based solar cell. Is it efficient? Yes, it's efficient, because you see in this slide, fine, this is based on experimental observations to a good extent, and you see silicon solar cell is efficient. So yes, this makes sense. PN junction solar cells, yes, this we had talked about, but it does not talk about the design aspect of this P plus N, N plus P. So even when the question does not explicitly say, assume those things. Okay, it makes analysis better. It helps you revise the concepts while you are solving a problem. All right. So everything is given. There's nothing much to be done here, to be honest. So KT by Q ln 1 plus IL. IL is your photocurrent, or the light current in light, or short circuit current. That is 15 milliamps is given. 15 milliamps divided by reverse saturation current is given as 3 nanoamps. 3 nanoamps. KT by Q we know is 26 millivolts, because we are operating at the room temperature, 300 Kelvin. This is a good figure to remember. ln 1 plus this will be 5 into 10 to the power 6. So we can simply drop the 1 because it's it's not going to play much role. So let me ln 5 into 10 to the 6, this is 15.4 times 26 millivolts. This is coming out to be 0.401 volts, 0.4 volts. Fine. Okay, so in this problem we had obtained this much of open circuit voltage. Let me just draw the IV characteristics once as to where we are lying. So this is, so in the dotted we have is your dark solar cell, so to speak. Right, and now what I'm going to draw is when we have shine light. So this is in a solid color. This is the VOC, 0.4 volts. This is what we are talking about. What was it? 15 milliamps. This current over here is what? 3 nanoamps. So essentially a good way in fact to see IV characteristics is to put current in log scale, because 6 orders of difference you will not be able to appreciate here, and this problem will become more prominent when we talk about the next sets of devices, the photodetectors. There, because you see that the change in order is in fact 6 times rather, or 6 times at least. So such kind of orders, such kind of change in magnitudes are not perceptible to a good extent. Okay, so this is that, and finally again you can form the fill factors and whatnot, but that's not what the goal of this problem was. But my idea was to highlight this: whenever there is a large change in magnitude, when you're changing something, for instance here we're shining light and this changes, right? It's a good idea just to have this in the log scale. X-axis should be in linear because it's not changing from 0 to 0.4, let's say. This is not too much, not too big of a change. Okay. Yeah, so I believe this is the last problem I have for the section on solar cells. So again, we have a p-n junction solar cell, short circuit current is given, open circuit voltage is given, and we need to find the fill factor. So fill factor essentially how much of the rectangle is filled, and the solar cell we are operating at 0.5 volts and 10 milliamps. Okay, so let me just try to solve this first, and then we'll analyze. So PM is nothing but VM times IM. VOC, ISC, this is I versus V. Sorry about this, 1 second. This is VOC, and we are VOC is given 0.7, and so we are operating at somewhere here. This is the operation point. So I'm writing this coordinate VM comma IM. Different ways to write this. So VM into IM is given as 0.5 volts times the current that is flowing is 10 milliamps divided by open circuit voltage is 0.7 times the short circuit current is 15 milliamps. So that would be 2 and 3. Yes, so should be around 0.5. Yeah, 1 over 2 is 0.5, so this will be approximately 0.5. 50%. This one. So this is only so to say 50% fill factor with which you are operating. You can try to push it. Let's say we change. Let's do that. In fact, now we try to change it. Let me try to change it to a different point. Let's say I'm now making it VOC as, let's say, 0.4 and ISC is, let's say, 12 milliamps. Will it be any better? Let's see, fill factor 2 I'm calling it. So VM is 0.4 times 12 divided by 0.7 times 15. So this will be 4.8 divided by 10.5. I think it will be inferior. 4.8 divided by 10.5, 0.46. Not much better. Sorry, not much worse, but there is a way actually to find out the optimal point at which fill factor is maximum. How do we do that? We do that because, for instance, we do know screen. So we know VOC, the expression for VOC, right? So VOC will be your KT by Q, which is a constant at a given temperature, ln 1 plus by IS times I photon. This ISC is nothing but the I photon that we have, right? So this is your VOC times ISC. What you can do is you can play around with different parameters. So photon is the GOP is essentially that depends on your the optical generation rate. That depends in turn on the spectral density that you have. Often that's not under our control, but what is under control is IS. Okay, so and remember this also has a term for the, if I remember, for this this current, this short circuit current has a term of diffusion length over there, and this also has diffusion length. That's where there are some ways in which you can try to find out what is the optimal operation point. That's not the point of this problem, but I saw this, that we need to increase the fill factor to the maximum. Just a thought came into my mind. Okay, right. Oh, wait a second. Maybe you cannot change. Oh yeah, VOC and ISC I believe you cannot change once you have fabricated it. So this will not change, but PM, because this lies on this line, and so we know the expression for this line. Remember that that it was, the total current was the I naught e to the power q VA over KT minus 1. That's the PN junction current, minus area times GOP times W times ln. So if you can just try to find out that where this maximizes. That's an exercise you can do. I remember my professor asked me to do such thing once. Okay, so now coming to the, how much time do we have? Fine, we have 20 minutes. I think we should be good. So now we come to the second optoelectronic device for today, that is the photodiode. So again, this is the same diagram that I have from the previous discussion. Essentially this was a load here. This time I have now replaced, and I just wanted to ask this question: where do we bias it? The operating principle remains the same as before, that is, we're shining light, right? And so of sufficient energy, again I'll assume that h nu that we have over here, right, h nu that we have is greater than or equal to Eg. That goes on without, this is the assumption that I'm making. So electron hole pairs will be generated, and as you can see that there'll be an electric field, so they will be swept away. Now I do not want to drive any load here. I just want to detect. So detection, this is essentially used for a photo detection, to detect a photon of a given wavelength. That we can see, for instance, if the given photon for this material, if the energy of this specific photon is higher than the band gap, then it will be detected, right? But you can detect, I mean, too much. For instance, what I mean is that, so silicon band gap is 1.1 eV. Corresponding to that, the wavelength that comes out is around 1.1 micrometers. So any wavelength 1.1 micrometers or lower you can detect. So for instance, you can detect visible with a silicon based photodetector very, very comfortably, because our visible wavelength is 0.4 microns to 0.7 micrometers, right? But you can also detect UV, which is below, let's say 350 or let's say 300 nanometers. So the silicon photodetector will detect a large number of photons of varying um, frequencies, right? So this is important that we have to choose in such a manner that, because it will just create some, give us some spurious data which you do not want. Okay, we want to be as specific as possible. So this is, I mean, one of the practical issues that we face, but let's just forget about that for the time being. So here we will be able to detect any photon which is higher than the photon with energy higher than the band gap, right? So where do we bias it? That's the question that I want to ask. So first let us draw the our good old IV characteristics of a PN junction diode. We have this forward bias characteristics, and then finally I'm not talking about the breakdown and what, so let's just forget about this, assume the breakdown voltage is high enough. Okay, so this is the current that will be flowing in this circuit, and I'm not applying now I'm not applying any bias. Okay, and this circuit, as you can see, you will argue that this circuit is not complete. I mean, for a current to flow there has to be something here, a battery, a resistor, something has to be there. Let's just see, let me just say that let's just a load here, so I'm not applying any bias. So I'm still not applying any bias, just shining light. What will happen? The same thing, we had discussed this already. So when we shine light, electron holes pairs are generated, there's an electric field already is existing over here. The electrons will travel from to the right and the holes will travel to the left, and thus current will flow from n side to p side, which is the reverse current, as to so to speak, right? So this implies this will be added to this current. Okay, so the current that is shown in the red over here is what we called is I dark, when we are not shining any light. So this is essentially the characteristics of a typical PN junction diode. Okay, now I'm shining some light. Let's say light intensity is not too much, it's moderate, let's say. Okay, so what's going to happen is that the current will increase, right? Because this current now, the current due to shining of light, electron hole pair which have generated, now they can flow in this circuit. So what's going to happen, everything will shift, will increase in magnitude. So the current, let's say, actually I have only argued that this point has shifted. Now we apply the bias, right? So a PN junction also, PN junction current will also come to the picture. So this will, second, so I'm shining some light, and this is how the behavior will look like. Why this shape is retained? Because when you apply any biases, all the diffusion mechanism that is happening in a typical PN junction, that will still hold on, especially when you are forward biased. In the reverse biased, however, only the reverse saturation current flows, but the key change that you will notice is that the reverse saturation current will be increased now many folds. It will not just be the reverse saturation current, but some photo current. Okay, now let's say you increase the intensity, that is, you increase the number of photons that are falling, and let's just assume that due to this more number of electrons falling, more number of electron holes pairs are generated. That's an assumption. We'll try to quantify it a bit, but let's just say that is the case. So if I increase this even further, right, more electrons falling, what's going to happen? More photons falling, more electron hole pair generated, the current will increase even further. And again, if you extend the discussion that the PN junction diode characteristic, the form will remain the same. It will go something like this, right? So that's how so this is how the IV characteristics will look like. Okay, and let me just draw one last one. When let's say you are shining the huge number of photons, so it will look something like this. So what is happening is that when you're moving in this direction, this is number of photons increasing, and the assumption that I'm making is that as the number of photons is increasing, more number of electron hole pairs are being generated. So that is an assumption that I'm making. which I believe through the first order you'll agree. Okay, why I put this question mark here is just to illustrate that first I'll talk discussion only when we are applying zero bias. So I'll just talk about when we are talking only in terms of the effect of light. So you see what I mean is that this point will now get shifted to this point, and this point, and the rest of the characteristics I drew, I just superimposed. So the total current again, like before, will be I, the typical PN that we have, plus I light or I photo current. Okay, so this we know is I naught or IS, exponent of QVA over KT minus 1, and this negative direction denotes that it's flowing in the opposite way, which we see here, and this is the photo current, and I believe QA GOP W into D. Again, it's not so simple in the sense that sorry, not just that W plus ln plus LP, all that term is there. We'll come to the expressions a bit later, but the way how to understand the working of a photodiode is by this. You just try to find out these points, the photo currents at zero bias, and that will give you a reference point, and from there you can draw your IV characteristic. The mathematical expressions that's behind the scenes is this one. Okay, so then typically what we do is that we do not operate it in the forward bias. Why we don't? And excuse me, why we don't do that is essentially, so you see the current here is already in a few milliamps. I'll now put some numbers. The forward bias current that we have seen in our problems is a few milliamps. The reverse saturation current seen is a few nanoamps, and the photo current that you see again in the previous problem was a few milliamps. So in the forward bias, few milliamps of reverse, a few milliamps of photo current plus few milliamps of your, let's say, the diffusion current, you will not be able to appreciate which component is coming from where. However, on this, in the reverse bias side, we can appreciate it much better, because the majority, in fact, a heavy majority of the contribution will be coming only due to the presence of light, not due to the contribution from the reverse saturation current or this exponential term, because it's negligible here. That's why we operate the photodiodes in the so-called third quadrant over here. We apply this as a reverse bias. So now I can comfortably say that what we have here is this P terminal is connected to the negative one, and this something like this. The reason so this question mark, I hope I have answered that why we operate in the third quadrant. Okay, and how does it look like? So when we operate in the third quadrant, again you see that just at the boundary of the depletion region, the carrier concentration will be up to one diffusion length will be negligible, and that's why this is again borrowed from just your reverse bias PN junction. There's nothing that is happening except for the fact that light is also shining over here. Okay, so what is the depletion length to consider? So whatever is falling in the depletion region, naturally that can contribute to the current, that will contribute to the current rather. However, in addition to that, anything which is in the one diffusion length on either side, right, they can be swept away because they can diffuse in the depletion region, and thus they can also contribute to the current. So all the photons which are falling under W plus ln plus LP, hence this expression, okay, they will contribute to the current. Fine. Let's now try to, this is just a problem which just builds up on the discussion that we have had till now. 1 second. So if you want to use photodiode as a photodetector, right, so photodiodes, there are multiple flavors of that. Okay, so photo essentially means photon and diode. So in fact you can also argue that solar cell is a photodiode because it's a diode, PN junction, and it's related to somewhat to a photon, right, and an LED. So that's why to this specific, to be more clear, this is a photodetector application that I've been talking about. Okay, it is invariably reverse biased. Why? So the power consumption must reduce comparable to the reverse bias condition. Here we have not yet talked about the power consumption. There will be some power because you will be supplying this much of V reverse, right, and the current flowing. So this part is not necessarily true, because the current that we are getting here is few milliamps, comparable to the forward bias. So the power and the voltage that we apply is also compare. So this is not true, is not much reduced. It's in fact it will be more or less similar. Second option, electron hole pairs can be produced by the incident photons only if the photodiode is reversed. That is absolutely not true, because all the discussion that I have had here till now was, I have assumed it to be zero bias. That's why this black dots that you see. The photons, the electron hole pairs will be generated irrespective of the bias. It's just the bias dictates where is the electric field lies and what is the strength of the electric field. That's what the bias dictates, right? Electron hole pairs will be produced irrespective of bias. The only condition it should have is h nu should be greater than equal to Eg. So this is also incorrect. Light variations can be converted into current variations only in the photodiode is reverse biased. So light variation, I mean by that they mean this different, this the black red and then green, blue and then violet. This is the photons variation. Light variation, you can see it's changing the current. Current is being changed here also, right? So this part, that light variations can be converted into current variations only if the photodiode is reverse biased. That is not true. Even in the forward bias you see the variations. It's just that these variations, when you put it numerically that okay, this much percentage has changed, it will be difficult to deconvolute. Here it's much more straightforward. Okay, so this is incorrect. Forward bias, you also see the current variations. When the photons are incident on the diode, the last option is, when the photons are incident on the diode, the fractional change in reverse current is much greater than fractional change in forward current. That is what I meant here. It's from nanoamps, it will go to a milliamps. Here it will go few milliamps to few milliamps. So the fractional change is much larger, the percentage change is much larger. The fourth option is the correct. Okay. The maximum wavelength of photons that can be detected by a photodiode made of semiconductor band gap of 2 eV. So we need to find the maximum wavelength of photons that can be detected. So it's very simple that, so the photons to be detected, that means the max. Why it's putting a maximum limit? Because if for below that, sorry, one second. So h nu must be greater than equal to Eg, or we can see hc by lambda must be greater than equal to Eg. So for instance, you can see lambda must be less than equal to hc over Eg. There is an upper limit that this material how much it can detect. All right, and it's the same expression, just put the value of h and c. This is the expression that we have been using. So 1.24 over so I'll say lambda should be less than equal to 1.24 over Eg. Eg is given as 2 eV. So lambda should be less than equal to 0.62 micrometers, 620 nanometers. Straightforward thing. If there is a band gap, I mean EV and EC, and you want to excite this electron from here to here, you must supply at least Eg, which is written over here. Okay, right. So now, okay, so there are a few figures of merit. This means some terminologies which we encounter. So there's a key term called the external quantum efficiency. Okay, let's just understand what this means. Is essentially external quantum efficiency. So the output here is the current, right? So this is essentially the electrons coming out, electrons or holes, but I'm just writing electrons coming out divided by, this is the input. It's a photodetector, so the input is in the denominator, and the current is in the numerator. Okay, this is also written as by the way eta EQE. So the electrons coming out, how are we measuring them, right? So we are measuring them in terms of the current that is coming out. So this is the I photo current, right, divided by the photons that we are shining, right? So the photons that, just a second, let me just see if I have an expression. No. Okay, so the electrons that are coming out are given by this I photons, right? And just a second, because this has to be neutral, or do I say um, this has to be what's the term I'm doing? This has to be dimensionless quantity essentially. So I'm missing some term. Just give me a minute. External quantum efficiency. This is the I'm sure that this is the this is the concept that is behind it, but let me just see if I can find the expression. Just give me a second. Yeah, okay. So so how do we write this? Is that the current that is coming out, so electrons will be current divided by charge. This is per unit second actually, that's why I was confused. Photons shined per unit second. Okay, the photons shined, so that will be given as the power of the power of light that you are shining, right? So that power is essentially your energy, h nu, divided by the time per unit second. Okay, so nh nu rather, n is a number of electrons, h nu is the energy of one photon per unit time, right? This is your optical power. If you want to obtain the number of photons per unit second, this will be pop over h nu, simple as that. Okay, the electrons that are coming out divided the photons shined per unit second. So this is the expression this is the expression that we have for external quantum efficiency. There's one more thing called the internal quantum efficiency. That would essentially means electron hole pair generated per unit second, obviously, divided by photons reaching depletion layer. So you'd say, okay, why will the photons be lost? Because please remember, when we grow them, we have already talked about this, there is stack, P plus stack, or P stack that is sitting above the top. It will absorb some photons that are coming on the surface. So alternately, I can also see that eta EQE is equal to eta IQE times eta of transmission. This means photons have to be transmitted over the P layer times eta collected. Why? This is because some electrons will be lost. They're generated in the depletion region, but they're lost at contact and whatever. So this term also comes in there. If we try to, because we can still try to play around with transmission and collection to a good extent. So EQE and IQE are more or less very closely related. Okay, the rest, the next thing we have is the responsivity of a photodetector. So responsivity is very closely related to, in fact, your this thing, what we call it, the external quantum efficiency. Okay, it just essentially it's just how to say this, it's a way of in a way you can call it as a normalization. What do I mean is that it's just that these first two terms, I'm just trying to remove them out of the picture and to leave just below the h nu behind. So responsivity is nothing but the photocurrent that is coming out divided by the power that you are inserting. Simple as that. It's very straightforward. So that's what I mean, that how how eta and responsivity are related, you'll see in this problem. So how are they related? If you see, let me write it here itself. So I can write this as IPH by POP is nothing but R, right? H nu over Q. Okay. Yes. So R will be written as eta Q by HV. Eta Q by H nu. So nu again you can replace hc by lambda, and this is the expression that will come. We just put in the numbers. Efficiency of only 1%. You see, it's a very bad device, so to speak, because external quantum efficiency is only 1%. Okay, fine. 0.01 times the wavelength has been given as 500 nanometers. So we have to put it in microns, because please remember this is in microns here. So this will be in fact 0.5 divided by 1.24, right? Yes. So this will be 5 into 10 to the power minus 3 over 1.24. That's 1.2. That's 4 times. Exactly 4 into 10 to the power minus 3. Again, units are amps per watt. So 4 milliamps per watt. This is the answer. Okay, and so this is how it typically looks like. So you see responsivity with respect to wavelength. It should follow ideally this straight line, but that doesn't happen, because please remember the non-idealities are always coming to the picture. It just falls off the cliff as we approach this, because there is I think it has to do with the absorption and due to the fact that silicon is not a direct band gap semiconductor. Okay, the last problem for today is we have a typical PN photodiode with an intrinsic width of 20 microns. So what essentially is happening is this is P, this is I, this is N. So this essentially whole thing is just a depletion region. Okay, we need to determine the quantum efficiency of the photodiode. So if you recall, as I told about if the light is falling here, let's say, right? So I've told you that IT divided by I naught or something given by e to the power minus alpha d or alpha t, the thickness, whatever that is. Transmitted is related to the thickness of the material, right? So here we want to know how much of it is being absorbed in this region, which is 20 microns wide, right? So this is the transmission one. So I can write the light absorbed, the I absorbed will be equal to I incident minus I transmitted. Yeah, that's it. I mean, there's nothing to underline here, because so yeah, okay. So if we divide it on both sides by the I incident, so what I get, I absorbed over I incident, say 1 minus I transmitted over I incident. This is the fraction. This is essentially your quantum efficiency. How much of it is absorbed of that is incident. This is the definition of efficiency, right? So I can write 1 minus, and this transmitted by incident is given by this e to the power minus alpha times d. Absorption coefficient is 10 to the power 3 centimeter inverse, and d is given as 20 microns. So you have to convert it into centimeters. So this will be 20 into 10 to the power minus 4. So minus 4. This all gets cancelled. So 1 minus 1 over e squared. E squared, so e to the power minus 2. 1 minus 1, so that's coming out to be 0.87. Okay, so this is the final answer. Hello? So this is our final answer. Okay, that is it for today. This is one more chart that I have, is how is a photon. So we have different, so as you can see, for a given length, if you have large absorption coefficient, the transmitted will decrease. So that's what you see. For a large alpha, the transmitted intensity has reduced, a much larger fraction, essentially pointing out the same thing. I've already talked about this before. This is just to complete the whole discussion. So that's all for today. Thank you for staying back. Thank you for listening. In the next session, we'll be talking about what's left, LEDs. Yes, and I don't remember after that what we talk about, but next week is LEDs. So make sure you join. I'll upload this video on the channel. Thank you for staying back.